the last time we met, we were looking at the fact that when there is a torque that is unbalanced, such a torque will produce angular acceleration. And our explanation was that for us to determine how much angular acceleration is produced, we need to we're using this in comparison with what we did for the linear motion. And what we saw was that the circular motion is going to be, it is going to be, we were going to introduce a concept of moment of inertia. We noted that the measure of rotational inertia, or the rotational inertia, depends on the following key things. And we listed 3 things. A, the shape of the object. B, the distance, or the location of the axis of rotation. And C, the mass of the object. This is what we noted when we were looking at this topic. We saw that the moment of inertia, or the rotational inertia, would depend on these 3 objects. So, for example, for the shape, we looked at a circle and a rectangle. For the rotation, for the location of the axis of rotation, we looked at a circle, 2 circles, one with the axis of rotation at the center, one with the axis of rotation at a different location. And we saw that. And then for the mass, of course, a heavier mass compared to a smaller mass. It is easier to rotate a smaller mass, an object with much less mass, than an object that is heavier. So upon discovering this, we now remember that we said whenever there is net non-zero force, torque, and it is non-zero, the object will rotate. The object will rotate, and the angular acceleration is directly proportional to the net torque. And that is, we saw that the net torque was directly proportional to angular acceleration. So this is what we said. And we have said moment of inertia, we are going to use the symbol capital I to represent the moment of inertia. The moment of inertia is the constant of proportionality for the equation that we saw here. So the constant of proportionality for this equation here will be the moment of inertia. Net torque will be equal to moment of inertia times angular acceleration. This is what we will find out now. Allow me to pause the class just briefly. I want to just do one activity, just a minute, class. We continue with the class. We are continuing with the class. We have just noted that the constant of proportionality is given by this equation where I is the moment of inertia. This is analogous to some net force is equal to mass times acceleration, where this quantity here is the moment of inertia. It is the inertia for rotational motion, similar to this one here, which was the mass, a measure of inertia. And when we talked about inertia during linear motion, we used the mass as the inertia. It is not really inertia because inertia depends on other things apart from just the mass, but it was the closest to the measure of inertia. Now, how is moment of inertia? For us to determine moment of inertia, how much is the moment of inertia? How do we determine the moment of inertia? Remember, it depends on the shape, the location of the axis of rotation, and the position and the mass of the object. So the moment of inertia, to determine the moment of inertia, you get the mass. When you get the mass and you have the axis of rotation somewhere, you divide the mass into small masses. Let's call this M1, M2, into the different masses, M4, M5. Then we determine the R1, the R2, R3, R4. Moment of inertia I is equal to the sum of M1 times R1 squared plus M2 times R2 squared plus M3 times R3 squared plus M4 times R4 squared plus whatever masses that you have made here, which is equal to sum of mi times ri squared. This is how moment of inertia is determined. You get small point masses, and then where mi is the ith point mass. There are some people who have not muted their microphones. Kindly mute your microphone, please, so that we don't make those noises that I hear in the background. Your microphone was muted automatically when you were joining, so it means that you are muting it deliberately, which is disturbing the class. Okay, so this is how moment of inertia is computed. I don't know who is making the noises.
Peter.
Peter Perry. Okay, so the moment, this is how we determine the moment of inertia. Now, what has happened for this particular course, we will not be using this formula to determine the moment of inertia per se, but rather what we shall do is that we will be told that we will be given the expression for the moment of inertia for a number of shapes that we shall encounter in this course. So we will have the moment of inertia for different shapes. So we have the moment of inertia for different shapes. And what we have is that, for example, the moment of inertia for a disk, e.g., a hoop, which is a ring. Natasha Kasongo. A hoop, we have a solid disk, we have a cylinder, we have, let me just say, etc. A different number of or different types of shapes that we shall encounter. And whenever we have a question that involves a particular type of object, the moment of inertia, the formula for the moment of inertia will be given. So in this case, here are the expressions for the moment of inertia for different objects, e.g. a hoop. A hoop. I for a hoop is equal to mass of the object times r squared. So if you are given an object, a hoop is an object which is a ring, all the mass is concentrated right at the edge of this. So it is a ring, like a you know, the wheel of a bicycle, of a bicycle, where we only have a ring like this, and the r is the radius. So this is simply a ring. It's also called a hoop. we also have the moment of inertia for is a solid, a disk. Now for a disk is similar to a ring, except that it has mass everywhere. So this is the disk. The radius is the radius of the disk from the center, from somewhere, the radius of the disk, R, and we have the disk of mass M. For a disk, the moment of inertia of a disk is given by half mr squared. I is equal to half mr squared, where m is the mass of the disk and r is the radius of the disk. This also applies to a cylinder. A cylinder has the same expression for the moment of inertia. Let's see. Make this go. Yes. Okay, I'm in a class, eh? I'm in a class. That is for a disk. Since a disk, if you get one disk here, you place another disk behind this one, place another disk behind this one, you form a cylinder. So a cylinder and a disk, they are very similar, and their moment of inertia is given by this expression here. Then for a solid sphere, like the ball, except that the ball is filled inside. We know that a football is has nothing inside, is empty inside. But let's have a football that is filled inside. It has complete mass inside. So that is a solid sphere. Mary Nyondo and Diversa Clement, kindly keep your microphone muted and please concentrate in class, because I can see that you are doing things that are not related to what we are doing now. He has left his phone by itself, or his gadget by itself, and is making noise in the background. So for a solid sphere, I said a solid sphere is like a ball, but that is filled inside, not an empty ball like a football. The solid sphere, the moment of inertia I for a solid sphere is given by 2/5 mass of the sphere multiplied by the radius of the sphere squared. We also have the moment of inertia for a rod. A rod that is pivoted at the center with axis of rotation at the central point, at the midpoint. So this is a long rod whose axis of rotation is at midpoint. The moment of inertia for such a long rod is equal to 1/12 multiplied by mass of the rod multiplied by the length of the rod squared, where L is the length of the rod. I don't know why people are unmuting their microphones when clearly the microphone was muted. Emmanuel Mwamba, you have a question?
Yes, sir, I have a question.
Yes, please, you can go ahead. Emmanuel Mwamba, you can go ahead with your question.
Oh, sir, I'm asking on the solid sphere there, is it 2 over 5?
It's 2 over 5.
Okay, sir, thank you.
Okay, thank you. So the moment of inertia, then we also have a long rod, number E. It's again a rod. Now we have the axis of rotation at the end of the rod. With axis of rotation at one end. So let's have the axis of rotation at one end. This is a rod like this one here, like the one above, except that I am already recording the class, so there's no need for anyone else to record. The axis of rotation is at the edge of the rod. Yes, please. Irene Tembo, are you talking to the class or you are just making noise? So we have a long rod with the axis of rotation at the edge, at one end of the rod, like this. The moment of inertia for such an object is given by it is given by 1 over 3 mass times L squared. Where L again is the length of the rod. So we have different shapes that have different moments of inertia. These have been calculated for us. To understand what we've just done above, let us see, take an example, and the example is, let's get a 150 kilogram merry-go-round, a 150 kg merry-go-round in a shape of a uniform solid disc. So we will have an interruption after approximately 10 minutes from now. When we are interrupted, please log in again. Just use the same link. Join the meeting using the same link after when we get interrupted after 10 minutes from now. So let's write the question. The merry-go-round in a shape of a solid disc, horizontal, of radius 1.5 meters is set in motion by wrapping a rope about the rim. It is set in motion by wrapping a rope about the rim. Of the disc and pulling on the rope.
They make me upset. Oh, wait, Maurice. What is that?
So we have the merry-go-round that is set in motion by wrapping
Ungaika kusajja washobola kujja ku kigero kya.
Oh, Akig, please, you are making noise.
Akireki.
This is very annoying. Gentlemen and ladies, is it difficult to keep your microphone muted? So this is set in motion by wrapping the rope around the rim and pulling the rope. The question is, what constant force must be exerted what constant force must be exerted on the rope to bring the merry-go-round from rest to an angular speed to bring the merry-go-round from rest to an angular speed of 0.5 radians per second. Not radians, let's use a different set of units. To 0.5 revolutions per second.
Excuse me,
Yes,
sir. Sorry for interrupting.
Okay.
I think here where there is merry-go-round from, they're supposed to be laced.
To be from, okay, let's say,
From
what
rest.
constant force must be exerted on the rope to bring the merry-go-round from rest to an angular speed of 0.5 revolutions per second. So the situation we have here is a merry-go-round. It is pivoted somewhere at the center here. Let's put it like that. And this is a solid. It has a radius of 1.5 meters and it has a mass of 150 kilogram. And the question is, we get a rope that is wrapped around the rim. So we have a rope that is wrapped around this rim here. Here is a rope wrapped around the rim. And then you have the rope going like that. You want to exert a force on the rope so that the merry-go-round begins to rotate. You want it to rotate so that it rotates like that. The question is how much force must be applied in order to bring the merry-go-round from rest to a speed of 0.5 revolutions per second in 2 seconds. We know that this force here will cause a net torque which is equal to force times R sine theta. That's what the force is going to cause. Now, any radius of a circle makes an angle 90 degrees within the tangent. So that when we put 90 degrees here, this torque simply becomes equal to FR, because sine 90 is equal to 1. So this is how much torque is being produced by the force that is being applied. And then we also know that the same torque is equal to I times angular velocity. No, angular acceleration. So we can equate this here and say equals to I times angular acceleration. Thus, we are going to simply get force times R is equal to I times angular acceleration. From the information given, the time 2 seconds and the rest angular velocity is equal to 0 and angular velocity of 0.5 revolutions per second. When we mix these together, we can find angular acceleration, where angular acceleration is equal to final angular velocity minus initial angular velocity divided by time. So now, allow me at this time to quickly save what we are doing so that we don't miss anything. So I was just saving that. I mentioned that when we get interrupted now, we need to just log back in very quickly in the next 1 minute, less than a minute. The Zoom will go off. When it goes off, we'll please click the same link that you used to enter the class, and let's enter the class again, and we continue with the class. So I have just saved our board so that I can share our board with us when we are done. So I will allow the Zoom to. We will begin. When we come next, we will not have this board that you are seeing, and the question will not have it. You will still have it in your books. So just take note that we'll begin from this equation. Okay. So on the board, we had the equation force times R was equal to I alpha. And we had also seen that alpha is found by taking the final minus the initial angular velocity divided by the time, where we knew that the final angular velocity is equal to 0.5 revolutions per second. And the initial angular velocity was equal to 0 radians per second. At all times when we are dealing with circular motion, we must convert the units into SI units. So we need to convert the revolutions per second final angular velocity, which is equal to 0.5 revolutions per second is the same as 0.5 times 2 pi radians per second, because 1 revolution is equal to 2 pi radians, where 1 revolution is equal to 2 pi radians. So we are saying this is where 1 revolution equals 2 pi radian. With that, therefore, we can get our I as being equal to 0.5 multiplied by 2 pi radians per second minus 0 radians per second divided by 2 seconds. We can find this angular acceleration, and you should find an angular acceleration which is approximately equal to pi over 2 radians per second. When we use it now here, we get this equation. Now that we have we shall have F is equal to I alpha over R, where alpha is simply that. So we have pi over 2 radians per second multiplied by I divided by R. But we know what I is equal to. I for a disk, we can check from our from the equations that we gave above, that for a disk, I is equal to 1 over 2 mass times R squared. So that F is equal to pi by 2 radians per second multiplied by 1 over 2 mass times R squared multiplied by 1 over R. So we can now get this R, and this R will cancel out. And finally, you can put the mass is 150 kilograms, R is 1.5 meters, and you put the numbers there, you'll be able to find what the force, constant force that must be applied is in this case. So for any object that is under the action of some forces, we can take the net force. We must always remember that the net torque is equal to I alpha. I don't know why people are playing around with the, I'm already recording the class, please. So no need for you to request for recording. Kindly concentrate and take the notes. Write these notes in your own notebook. Stop playing around with the screen.